So whenever I first got started in gravitational waves, the experts tried to make it easy for me. And they said, a gravitational wave is just a ripple on space-time. You got that? There we go. Yeah, I didn't get it either. So what is space-time? Space-time is the universe. And the universe is made up of the 3 dimensions that we live in every day. The x direction, the y direction, and the z direction. So those axes that we were all taught about in school. However, those 3 dimensions are also fully united with time. It's inseparable. Time is not as constant as you think it is. So in order to make the idea of space-time easier to understand, we often represent it like a trampoline that has grid lines drawn on it. Whenever mass is present in space-time, it's going to make a depression in that space-time. So in the example I have up on the slide here, you see that the sun is making a deeper depression in space-time than the Earth is, and that's because the sun is more massive than the Earth is. Imagine rolling a ball on this trampoline example of space-time. If a ball passes near one of those depressions, the path of the ball is going to be deflected, just like if the ball was being attracted to the mass that's making the depression. Now imagine that you have 2 masses moving around. As those masses move around, you're going to have a change in the curvature of space-time. And those changes are going to ripple away from the source, just like a ripple in a pond. And that ripple is going to decrease in size the farther away it gets from the source, just like a ripple in a pond. This is what a gravitational wave is. Gravitational wave, very simply, is a change in gravity traveling throughout the universe. That's what the experts were trying to simplify for me whenever they said gravitational waves are ripples on space-time. So this is really profound. You and I, we have mass. The scale tells us so. Some of us have more mass than we would like. But either way, we have mass. And we happen to be in the universe. And the universe is space-time. That means every single one of us are making a depression in space-time. So how does a gravitational wave affect space as it passes through it? If we want to detect a gravitational wave, we need to know how is a gravitational wave going to feel. Well, as a gravitational wave passes through space, it's going to compress space in one direction, say side to side, and expand it in the other direction, say up and down. And as the gravitational wave passes by, this expanding and contracting is going to alternate back and forth. So a gravitational wave has the effect of squishing and expanding and then changing the direction of that squishing and expanding. As a matter of fact, if you were close enough to a very strong source of gravitational waves, this would hurt. This would hurt so much that you could be ripped to shreds. And this has a real scientific term associated with it, and it's called spaghettification. Why is it called spaghettification? Because you could be stretched so far up and down while you are squished side to side that you'll be stretched out into a noodle until you're ripped apart. So instead of finding gravitational waves from here on Earth, we look out into the universe for some of the most massive, violent, energetic events that happen out there in the universe. Luckily, none of those are next door to us. You do not have to worry about getting spaghettified by a gravitational wave. However, That gravitational wave from the universe has traveled vast distances by the time that it gets to us. And it's getting weaker all along the way. So you will not be able to feel a gravitational wave. So we need to build a detector that can feel a gravitational wave for us. That detector that we've built is called LIGO, and the National Science Foundation has made it possible for us to make this a reality. So I keep talking about this weird word that is not in the dictionary called LIGO. It's an acronym. So every letter stands for something. Let's break it down. First is the L. It stands for laser. We use laser light to make the measurements to look for gravitational waves. The next one, I, is a little bit harder. It's a big word. It's called interferometer. And you can pick apart this word very much in the same way that you pick apart the word thermometer. So, ohmometer means that this is an instrument to measure something. Therm refers to heat or temperature. So a thermometer measures temperature. An interferometer, so we see a thermometer in there, it's measuring something. We're referring to our measuring device. The interfer refers to what is it that we're measuring. What we're measuring is how light recombines with itself, how the laser light in the L recombines with itself. That is the main function of our detector, to measure the recombination of light to look for gravitational waves. Next is the most important letter, and that is observatory. LIGO is a new kind of observatory. We are not about making one detection, calling it a success, and then going home. Instead, we want to make many observations to learn more about the universe that we live in. Oftentimes, whenever I talk to people and I talk about learning about the universe, they say, "Who cares? I live here on Earth." Earth is part of the universe. You are part of the universe. Learning more about the universe can actually have implications for us in our everyday science. And what we're doing is, this is an observatory for gravitational wave astronomy. We are not looking at the universe with telescopes. We are not looking at the universe in any form of light. We have no pretty pictures like the Hubble Space Telescope produces. We instead are recording how the universe feels. And that is the essence of gravitational wave astronomy. How do you build a detector to feel these gravitational waves? We know how the gravitational wave is going to feel. It's going to squish in one direction, expand in the other, and go back and forth like that. So we built an L-shaped detector to take advantage of this squishing and stretching. We built a very large L-shaped detector. Each side of LIGO is 4 kilometers long, and in our everyday experience, that's almost 2.5 miles long. So what does LIGO look like? This is the LIGO that's in your backyard. So if you take a good look at it, you see lots of beautiful, lush, green forest surrounding it. We have another LIGO in the United States, and it's in the high desert of Hanford, Washington. So you look at this one, you see a very similar detector, but a very different environment. Instead of lush and green, you see brown and desert. Even though the environments surrounding our detectors are very different, what's inside our detector is almost exactly the same. So let's take a peek inside of how one of our interferometers work. So we fill the interferometer with laser light. If the arms change length, the output at our detector changes. The brightness of the light changes. If we take a closer look, the laser light goes into the corner where it's split into 2 equal pieces. It travels 4 kilometers down each arm, is reflected by a mirror, and is recombined at the corner, at an instrument we call the beam splitter. And that recombination is what we measure at the output. Now, if the arms are changing length, the way the light recombines changes. If we take a closer look at the output, we can see that whenever the light is in sync with the light from the other arm, then we get a nice bright spot coming out of our detector. If the light is out of sync with the light from the other arm, we get a dim spot. This is what interference means. This is the direct addition of laser light together, or any kind of light together. And if it's out of sync, if you add a +1 and a -1, you get 0. If you add 2 +1s, you get 2. And so the 2 would be our bright spot, and the 0 would be our dim spot. We measure the changing brightness of light that comes out of our detector. That tells us about how the length of our arms have changed compared to each other. And if the length of our arms change compared with each other, that means that a gravitational wave may be present. This is how an interferometer works. So we took a lot of time. We spent years operating our very first detector. And that detector wasn't sensitive enough to find gravitational waves. And we didn't expect it to be sensitive enough to find gravitational waves. Instead, this was a learning experience for us to figure out how to make a better, more sensitive interferometer. Once we took those lessons, we built a new detector. We took everything out of what was inside of LIGO and we replaced it with new, more sensitive equipment. We now call ourselves Advanced LIGO. And on the very first day of using Advanced LIGO to look for gravitational waves, in the very early morning hours, so 10 till 5 in the morning, this signal came through the LIGO Livingston detector. And we saw the same signal in the LIGO Hanford detector. You can tell here that there is something special going on. This looks the same. This is the very first direct detection of gravitational waves ever made. The biggest change in this graph, so the biggest up and down change, it looks big. But it only changed the length of our 4-kilometer long arms. Remember, 4 kilometers is about 2.5 miles. It only changed the length of our 2.5-mile long arms, 1/1000th the diameter of a proton. So less than a bit of matter that makes up part of an atomic nucleus. We are making the smallest length measurements humans have ever made just to look for gravitational waves. And if you take this signal and you put it through a speaker, you can hear it with your ears. So gravitational waves do not make sound. But if you take their signal, you can make it so you can hear it. So this 1/5 of a second signal, this 1/5 of a second sound you're about to hear changed everything for us. That low roar that you hear in the background is the noise that we are always collecting with our detector. That thump was the gravitational wave. And you can't hear a lot of detail out of that thump. So what we did is we increased the pitch of our gravitational wave so that you can hear more detail. And remember, this gravitational wave only happened once. We're playing it 3 times for you so you can listen to different parts of it. So let's listen to it again with its pitch shifted up. This was incredibly exciting. So we spent the next 5 months playing devil's advocate. We tried to prove that this isn't a real gravitational wave. In those 5 months, we measured our confidence that this is a real gravitational wave. We extracted science from this signal, and we published our results. So what did we find? First of all, the shape of this signal, which translates into that whoop sound that you heard, that is a signature of 2 bodies going around each other. And as they get closer and closer together, they orbit each other faster and faster and faster until they merge into each other. This is the same effect as whenever a figure skater starts spinning with their arms out. And then they spin faster and faster as they pull their arms into their center. It's the exact same physics going on. So the fact that we heard this whoop sound, we knew were 2 bodies coming together and merging into one. Further data analysis revealed that this was 2 black holes, each 30 times as massive as our sun, but the size of cities, and 1 billion light years away from us. As they were going around each other in this signal, they were orbiting each other over 100 times a second. Imagine that. Something that is each 30 times the mass of the sun going around each other 30 times every second. And just before they collided at the speed that was a little bit more than half the speed of light. And in just this 1/5 of a second signal, more energy was released in gravitational waves than in all of the light from 500 billion Milky Way galaxies. Well, after this detection, we went on to make 2 more detections. One was on Christmas night of 2015. That was an awesome Christmas present. The other one was announced just 2 days ago. I'm very excited that the press conference happened before this talk. Otherwise, I wouldn't be allowed to tell you anything about it. So on January 4th of this year, we detected another gravitational wave. And all of these gravitational waves have been from black holes merging together to form a bigger black hole. So what are the accomplishments for making these detections? This is the very first time that we have directly observed a black hole. Before this, we were able to infer the presence of black holes from X-rays produced by gas and dust being compressed and heated up as they approach and entered a black hole. That's what all of those purple black holes you're looking at are. Those are the black holes we observed with X-rays. Now with gravitational waves, and those are the black holes that are blue on this chart, those are the very first black holes that we have directly observed. This is also the very first time we've seen black holes coming in pairs. And this is also the first time we've seen a pair of black holes merging into one. After they merge into one, these have produced the largest known black holes of their class. And this class is called stellar mass black holes. Stellar mass means that these are the corpses of the most massive stars that whenever they died, they collapsed into a black hole. And these are the largest known stellar mass black holes. Every time humans have looked at the universe in a new way, we found something we never imagined to look for. And that new thing, that unexpected thing, usually revolutionizes our understanding of the universe. And I want to be a part of that revolution. What secrets will the universe reveal to us in gravitational waves? I don't know, but I do know that it's going to happen in your backyard.